And without further ado, Michael Schwartz, Daniel Gruss, and Moritz Lipp.
Hi, and welcome to our talk, Meltdown, Basics, Details, Consequences, where we talk about one of the infamous CPU vulnerabilities of January. My name is Moritz Lipp. I'm a PhD student at Graz University of Technology. You can find me on Twitter, write me an email, or talk to me later on.
My name is Michael Schwartz. I'm also a PhD student at the same university in Graz. I'm also on Twitter. You can write me an email, talk to me afterwards. I'll be here for the rest of the conference and DEF CON.
And my name is Daniel Gruss. I'm a postdoc at Graz University of Technology, and you can also reach me online. We also had a lot of other people who contributed to this work. Anders Fogg, Daniel Genkin, Werner Haas, Mike Hamburg, Jan Horn, Paul Kotscher, Stefan Manger, Thomas Prescher, and Yuval Yaron, who are not here, but this was a great collaboration with them, and yeah, we're looking forward to working with them in the future.
Yeah, so let's dive into it, and we start right off with reading kernel memory from user space, because that's pretty straightforward. Right, Michael?
Right, so we have our virtual address space in our application, we have our user space, addresses all mapped there, we have the kernel mapped in our application. So why not read something that lies in the kernel?
Yeah, why not? So we just pick an address, like the Linux banner, get the address from that, and since every one of us knows C, we can do some simple pointer magic, use the address, cast it to a character pointer, dereference it, and then we can just print out the character located at this address.
So this sounds really easy, so let me try this. I compile your code, I run your code, see what's happening, and it doesn't seem to be that straightforward. It segfaults when I do that.
Yeah, that's not really surprising. You can't just access kernel addresses. It's working as intended. Kernel addresses are not accessible, and that's how it's supposed to be. Any invalid access will throw an exception, and it will lead to a segmentation fault.
Yeah, but there's not an issue, because whenever you have an exception, you just catch it and then continue your code. So that's pretty easy. We just install a signal handler, so whenever this segmentation fault occurs, we jump back and continue our next instruction.
Is that how you always deal with errors?
Yeah, that's what you're supposed to do, right? And then we can just read the value.
I don't think that's how it works, Moritz, really. So I tried that and still I get no kernel memory there.
Okay.
So maybe this privilege check actually seems to work and we cannot just access stuff from the kernel. And it doesn't seem to be that straightforward as you thought it is.
Okay, so maybe we should go back to the start. Maybe we should go back to operating systems 101, back to the basics. And there it looks like this. We have the user space, we have the kernel space, and they are isolated from each other. The user space can't just access the kernel space. And this isolation is a combination of hardware and software. And user applications can't just bypass this isolation. It's a huge wall that can't easily be crossed.
And there's also a fundamental concept of all the modern operating systems and systems we use. So we have this virtual address space with just virtual addresses. We usually call them just addresses because we have no idea about physical addresses when writing programs. And the CPU helps us with this virtual address space to isolate our process from all the other processes running on this computer. And then we have this physical memory, and the operating system manages that, and there is this mapping that the CPU uses to translate virtual addresses to the actual physical address frame. And this technique is our virtual address techniques. We have page tables for that. We have a lot of tables in memory. The virtual address is used by the CPU to index this table, so it's split into multiple parts, used as indices to these page tables, the multi-level structure. And at the last page table, then we have a page table entry that actually maps the physical page to this virtual address. And now we can zoom into this page table entry because it's quite interesting what's in there.
Yeah, and if we look at the different bits here, we have the present bit, the writable bit, user space accessible, write through, uncachable, reference, dirty, size bit, global bit, and the non-executable bit, some ignored bits, and the physical page number. But the most interesting part for us here is the user space accessible bit, because this defines that an address cannot be accessed by a user space program. If this bit is not set, it cannot be accessed. And this should be set for all kernel addresses.
Yeah. But in addition, what we need to know is that typically the kernel is mapped into every address space. And in addition, we have the direct physical map, which maps the entire physical memory also in the kernel. So as we can see in this picture, there's two virtual addresses mapping to the same physical memory. So maybe we can use those addresses to read the memory from. So to summarize, when we want to load an address, we come to the permission check, and either we have the permission to load the data, so we are fine, then we load the data and can use it, or the permission check fails, and then we simply crash. But that's what we see on the architectural level. But there are other attacks which allow us to see and observe things that we wouldn't do intentionally. And these attacks are called so-called side channel attacks. And so safe software infrastructure, if we have programs which do not contain any bug, this does not mean necessarily that the execution of those programs on our CPUs are safe. Because information itself can leak from the underlying hardware. And those side channel attacks then exploit this unintentional information leakage by observing those side effects. And this, for instance, could be the power consumption of the device. So depending on the key that is used, the device needs more power if it processes a 0 or a 1. Or the overall execution time of the algorithm can allow us to observe the secret that is processed. In addition, we have those CPU caches. And maybe those can also be exploited.
Yeah, I think the CPU caches are an interesting topic, so let's talk a bit more about caches and the attacks with them. So if you look at a simple program on the left side, simple C code, just outputs two variables, and then we have our CPU in the middle and our DRAM, and the program has to output a value, like the variable I here. What happens? We have to get the value somehow. So first, it tries to locate this value inside the processor, in the cache, which is a really fast memory inside the CPU. If it's not there, because it was never used before, it has to be requested from the DRAM, and it has to be read from the memory. The memory then answers our request for this value, responds with the value, and it goes again back to the CPU, is stored there in the CPU cache, so if we need it again, then it will be faster, and then we can use it. For the second access to this variable, we see it's already in the CPU cache because we used it before. It's stored there for future access until it gets evicted by a lot of other data, and we have a cache hit there. We can read it directly from the CPU cache. And there's no DRAM access involved, so this is a lot faster than this tedious process of requesting it from the DRAM and waiting for the DRAM, which is a really slow memory. And this makes our programs run a lot faster. And we can even measure that if we have some measurement methods to measure really small timings, like we have on most of the CPUs nowadays, then we can really distinguish whether such a memory access comes from the cache or has to be served from the DRAM.
But if we have these timing differences here, we can probably exploit that in an attack, right?
How would you do that?
I would think of this situation here. We have an attacker program, a victim program, and they use some shared memory, some shared library. And this shared library, if one memory location in there is cached, it's cached for both. And if the attacker now continuously flushes this memory location, it will be not in a cache anymore. And only if the victim accesses this memory location, then it's in the cache again. And the attacker will also frequently re-access this location. And when the attacker observes a fast memory access, the attacker learns that the victim has accessed this variable in the meantime, and if the attacker observes slow access time, then the attacker learns that the victim probably did not access it.
So we can see whether someone has accessed some specific data element.
Exactly.
Great.
So this is pretty low level already. So when we think about programs, we have a certain architecture, we have an instruction set, and the instruction set is just an abstract model of our computer that we use. It could be either x86, ARMv8 for instance, or Spark. And it serves as an interface between the hardware that we're using and the software that we are writing. And when we talk about microarchitecture, we talk about the actual implementation of the instruction set. And as we know, we have many different CPUs, therefore we have also many different microarchitectures like AMD Ryzen, or the Intel Core CPUs, or the Intel Xeon CPUs, and so on.
So if we now think back of computer architecture 101, how does it actually work if we have a program? What does the CPU do? And then we have this pipeline there where we have multiple stages, and first we fetch an instruction into the instruction cache, then we decode this instruction, execute the instruction in the execution unit, and we can do memory accesses and update the architectural register files. And we can do that in a pipeline. So if we are done with the first step, with the fetch step of one instruction, we can already get to the next instruction and fetch the next instruction. So we can pipeline that thing, and that makes our program go a bit faster because we don't have to wait for one execution to be finished when we start the next instruction. But all instructions are executed in order, so in the same order as they appear in our program. And if we have some dependencies that we cannot fulfill in the execution, then we have to stall there and wait until this dependency is resolved for this instruction so that it can continue. And if data is not cached, we need to wait for the DRAM until it's in the cache.
But if you think about this program, for instance, here, there are many things you can parallelize here, and some have dependencies. So it would be very clever to parallelize these steps and only run the parts that depend on previous computations at a later point, right?
Yeah. So not only does the compiler change the sequence of the instructions that are executed, also the CPU itself can optimize that. And when we have such a CPU who does that, we talk about out-of-order executions. So we now have two sides, the front end on the top and the back end on the bottom. And the instructions are fetched and decoded in the front end. And then they are dispatched into the back end. And there we have multiple execution units that then process those instructions. This means that we can now execute instructions out of order, and they just now need to wait until the dependencies are ready. If they do not have a dependency, you can execute them right away. So this means that in your program, you can have instructions that would occur later, but are executed before other instructions, because the execution unit has time to work on that instruction. But the most important thing is that those instructions are then retired in order, because otherwise the program would do something different, what the programmer did not intend the program to do. And only then, when this instruction is retired, the architectural state becomes visible. And when an exception occurs, they are checked during the retirement, and then the pipeline can be flushed, and the CPU can recover from a sane state that it had before.
So although this is called out of order, this means architecturally it looks like everything is executed in order.
Yes, because it's happening on the microarchitectural level. So on the architectural level, everything is the same, and you just don't know how the CPU is built. But since the state only becomes visible architecturally, what does this mean on the microarchitectural level? So I have a good idea. We can change the code from earlier to my new code. Because I'm good at programming, we start right off with a null pointer dereference.
Wait. What are you trying to do here?
Yeah, so first I'm just dereferencing the address 0.
Why is there even a volatile in there?
Yeah, because when I wrote the code, the compiler said this statement has no effect. So it would optimize the code away.
So you really want to have a null pointer there, which crashes your program?
Yeah, why not? Makes sense. at least to me.
So my static code analyzer is not happy with that. It says you have a null pointer now.
Yeah, who cares about code analyzers? There are so many false positives, like in this example. So at first we're dereferencing the null pointer, and then we just access an index of an array.
Okay, so it crashes.
Who cares? You can just catch the segmentation fault. And if we look at the flush and reload attack that Daniel described earlier, we can now just iterate with the flush and reload attack over the entire array, and boom, you have a cache hit.
So your unreachable code line, which comes after the null pointer, which should crash the program immediately, was actually executed.
Yeah, I told so by using volatile. It has an effect.
And we can see that in the cache.
Yeah.
So the exception was too late maybe, so it did something, although it should have crashed already.
So that's interesting. That means that out-of-order executed instructions leave microarchitectural traces, and that can be some state of the cache. It can be other microarchitectural elements that are brought into a different state, but it can also be some concurrency effect. We give a name to such instructions. We call them transient instructions because we somehow execute them, but then they vanish before they are actually architecturally made visible. So we can, through microarchitectural side channels, then observe the execution of these transient instructions. We found on December 3rd, we were quite busy around that time because we were still busy with the research on the other Black Hat talk we had earlier by that time. But on December 3rd, we decided, okay, we should probably prioritize this and look at this now. And then we looked at this independently, and all three of us came up with an implementation of the Meltdown attack, and we discovered that it actually worked.
So the only thing that we need to change from my code example earlier is, if you remember the first example that we had, we just used the address from the kernel and dereferences it. But this time, instead of using printf, we just access the array at the index represented by the byte that we just read. And then we do the same flush and reload attack again as earlier, mount it over the entire array, and check if there is a part of the array that is now cached.
So you say just adding another layer of indirection again solves all the problems, like all the time.
I do.
Okay, so let's try that. Wow. So I did that, and I got a cache hit.
Yeah.
Exactly at this index of the value at the address I dereferenced. So the index of the cache hit actually revealed the value that's stored there in the kernel memory. So the permission check was not fast enough.
It sounds like a huge problem.
And this is Meltdown. Meltdown is using out-of-order execution to read data from any address. The index of the cache hit reveals what data we read because we encode it through this cache side channel to transmit it from the out-of-order execution realm to the normal world. The permission check is not fast enough in some cases, and the entire physical memory is typically accessible through the kernel space. And we reported this to Intel on December 4 and then continued working in this direction. And one of the first things that I wrote on December 3rd, that was still, I wrote a tool to dump just arbitrary memory locations. Dump and dump memory, and yeah, kernel memory all over the terminal.
So we also brought a demo of this with us. We just start at a certain address and dump the memory. And in this example, the address is located at a position in memory where there is a log stored for the descriptions of the package manager installed on the system, and we just dump it. If there would be a key stored in there, we could also leak the key. So independently on what's written there, we can dump it.
But with the code that you showed before, we can only read a single character and then do the flush and reload, but it crashes immediately because it's still an exception that has to be handled. So how do you prevent the crash then to dump the whole memory?
So like in the beginning I said, when there is an exception, you just catch the exception. So we can just do fault handling to catch the exception, jump back, and try again. In addition, we can also do fault suppression by using Intel TSX, which we'll see pretty soon.
Yeah. When we got in touch with Paul Kocher through Intel connected us with Paul Kocher, he told us that he found something he called Spectre. And then we thought, okay, yeah, we can also use this to suppress faults, right? To prevent faults.
Yes, so with speculative execution, we can also prevent the fault in the first place.
So let's talk about this version with TSX, because I think that's one of the most beautiful versions of Meltdown. TSX is a really cool feature. It was designed by Intel to replace locking in certain scenarios, but we used it for a lot of different things already, because it has a really cool side effect of suppressing exceptions. You just start a transaction and do stuff whatever you want to do, and you can do illegal stuff in it, like dereference a kernel memory address, which would normally throw an exception, but the TSX transaction just aborts there and doesn't crash the application. So we can simply start a TSX transaction before we do all this meltdown magic. The transaction will abort, but that's fine, the program does not crash, and we get the memory, and we can do that in a loop and dump the whole memory with that.
Yeah, and that's
a really
quite
fast way. Yeah, because we don't have to handle exceptions like in an exception handling case.
Yes. Also, we can use, as said, speculative execution to prevent the exception to occur in the first place. So in this example, we have the speculate variable, which is just random modulo 2. And then, depending on the value written in there, we choose an address, which is either a valid address or the inaccessible kernel address. Then we have the if condition, and depending on what the value is, we either try to read from the valid position or not. But by mistraining the branch predictor, who does not know at this place, okay, do I go into that condition or not, because it hasn't read the variable speculate yet, it will at some point try to read the kernel address and then use the value to load the address stored at the index of the array, and then we have the flush and reload again, and then we can also leak the kernel memory.
We can even improve the performance by a really nice trick, by adding an additional null pointer dereference. We really
want to add null pointers.
Yeah, we really like our null pointers, so we learned to love them during the development. So in our code, we just add a null pointer dereference before we dereference the kernel address, so more illegal stuff in our application. And this is really cool because it makes the attack a lot faster and more stable, because apparently the null pointer blocks some exception handling, and we have more time to actually leak this value.
So this is all very nice, but you can only leak data that is in level 1 cache, right? Not anything else.
What if I told you that you can leak the entire memory contents with Meltdown? Okay, so what we saw in January and also before that, we had a lot of trouble convincing other people that we can actually read data that is not in the level 1 cache. It was assumed that you can only leak data that is stored in the level 1 cache. This was also what Jan Horn from Google Project Zero reported. And we tried a lot of things, and yeah, for example, we experimented by forcing the Meltdown attack to one processor core, and then on a different core we had the secret in the application, so they can't share the first level cache, the L1 cache, only the last level cache, and we were still able to leak the secret, so it can't be the case with the L1. It also works with the L3 cache. We also made sure that it's never in the L1 by constantly flushing the secret, and still we were able to leak it. It took a bit longer, so it was not that fast in leaking the values, but still we were able to leak values that are also in the level 3 cache, and of course also in the level 2 cache. And during this, Meltdown would even get the values into the level 1 cache for us in some cases.
But we can also got one step further by using uncachable memory. So we mark pages in the page table as uncachable, and this means that every read or write operation will go directly to the DRAM. So it will bypass the cache entirely. So we make sure it's not in the level 1, level 2, or level 3 cache. It won't be stored in the cache at all. And if the attacker is able to do a legitimate load of this value by either issuing a syscall that then uses this value on the same CPU core, the data still can be leaked. So we think that Meltdown might read the value directly from one of the fill buffers in this scenario, because they are shared between threads running on the same core. So one hyperthread can attack the other one.
So you can dump the entire memory, but it's horribly slow, right?
Yeah, but why would you all want to leak the entire memory? You have a lot of that. You just want to leak secrets. You don't want to leak everything. Just find something that you're interested in leaking and do a targeted attack using Meltdown. Not the entire memory dump, but something like, say for example, you use hard disk encryption, right? And use this VeraCrypt open source tool for disk encryption, and is a software tool. So at some point it stores the key of your hard disk inside the memory, and if I have that key, then I can get your laptop, decrypt your hard disk, and get all your interesting research projects.
But it would not be practical to search for that key, right?
It's just a small application, and we can find out where the key is.
So we actually did a demo on that. So on the right, you see a shell by a user called the victim, and he starts the VeraCrypt application of the recent version that you can download today. Then he will create a new encrypted partition stored on the system. So you pass the path where it should be stored, the encryption algorithm, the size, and then you enter your super secret password so that no one can read your data that you are storing in there. So we do that, we generate some random key by moving the mouse, and we just speeded up the video because otherwise the video would take ages to present. After that, the victim is going to mount the volume. So he needs to enter the password again, and then the volume will be mounted and he can use it on the file system. What the victim is going to do then, he will open the volume that is mounted in the file explorer and move his secret files in there. Now they are stored on the encrypted volume and no one else can read it. Until we start our exploit on the left shell. So we have the attacker user, he has no pseudo privileges, and he will create a directory at first where no files are in there, and then he's going to run our exploit. What the exploit does, it checks for offsets depending on the kernel version that is used, and then it's going to break KASLR. Because KASLR is active on the system, we need to first break it so that we can find the correct address of our identity mapping. Then there is a desk struct that we see later on, where we can go through a list to find the process which we want to attack. So we do this, then we can read either the entire memory of this process, or if there is no ASLR active, we can read the key directly. Then we just use this key to decrypt the volume and mount it using a tool or extract it to the file system. And now we have the files stored in the encrypted volume by stealing the key with Meltdown, and we can look at them. For instance, we can now get the credit card pin or watch the video that is stored in there.
Why did you show my credit card pin in the video?
And actually this is the video of our Black Hat's best song Pony submission last year.
Okay,
so using Meltdown, we can do targeted attacks as well.
Target something very specific. We have seen we have the de-randomized KASLR to access the internal kernel structures, but this is actually pretty easy because we have known values inside the kernel, for example a version string, a Linux banner, and we know the default address where it is located for every kernel version, and then we only have a really small entropy for the kernel address space layout randomization of just a few bits, so there are only 64 possible randomization offsets, and we just try them, read the value there, and if we found it, then we can de-randomize all the addresses and work as if we don't have any KASLR active.
Yes. And the next thing, like I said, the Linux kernel manages all processes in a list, and the head of the list is stored in the init task structure. And the location of this, it's at a fixed offset depending on the built kernel version. And if you know the kernel version of the distribution, you know exactly where that is, because it doesn't change for every user of this distribution. And each task list structure itself contains a pointer to the next entry of this, containing the process ID, the name, and also the root of the multi-page table.
Okay, so what we want to do is we want to resolve virtual addresses to physical addresses using the paging structures so that we can actually add this physical address to the identity mapping offset, to the direct physical map offset, and then read the values from there. And we can do that by just iterating over the paging structures of this process and then dump the corresponding pages. They might be in a randomized order, but they are 4 kilobyte blocks, easy to combine them. And we know how to combine them from the paging structures. The location, in other cases, the location of the key might be known if it's at a fixed address, for instance, because ASLR is disabled. And then we can, of course, directly just dump the key.
Yes. And then you know there is a key in this memory dump. Then you can use a tool like AES keyfind to extract the key from the entire memory dump. Then you can use, for instance, in our demo, PyTrueCrypt to decrypt the disk image and extract the data. But what's important to say here that this does not affect only VeraCrypt. This affects every application that stores the secret in DRAM.
The question now is who is affected, right? Which processors are actually affected? And
yeah, it's not only Intel. So Intel CPUs, most of them are affected back from many years ago, except for some smaller CPUs like some Atoms, they're not affected. For AMD, they seem not to be affected. At least we couldn't mount a Meltdown attack there, and we haven't heard of anyone being successful in mounting a Meltdown attack on AMD computers. For ARM, there are in the smartphones, and there's even one affected in the high-end smartphones, the Cortex A75. That was published in January as well by ARM, so this one is the affected core. You can also mount Meltdown on this core. And for other vendors like IBM, they have affected architectures like the Power architecture, Power 8, Power 9. You can also mount a Meltdown attack there. So it's not just Intel, it's many CPU vendors, many CPU models that are actually affected by this bug there. Apple CPUs are also affected. They said that all of their Mac and iOS devices are affected by the Meltdown bug.
So this is the list that was online in January, where all those manufacturers said, yeah, these are our affected CPUs. But in the end, there are also other CPU manufacturers. For instance, Samsung, with the Galaxy S7, introduced the Mongoose M1 CPU architecture, which has some interesting properties. And it was its first custom CPU design in the Exynos 8 Octa SoCs. And it has a perceptron branch prediction, a full out-of-order instruction execution, including full out-of-order loads and stores. What could this possibly mean? We can try to mount Meltdown there. So on the right, we have a root shell because we want to obtain the physical address, so we cheated there a bit, but that's okay, because on the left, we have a normal shell as a user. On the right, we start our secret application, which has a string contained, printing out the address that we then use in the normal user application. And as we can see, using the identity mapping, we can instantly dump the address stored there. But luckily, Samsung fixed it already. So if you have the latest update, you are good to go and Meltdown is fixed. But the latest update was published last month.
So that's half a year after.
It took them quite some time to actually fix it. So in the end, there are different CPU manufacturers as well that are also affected, and we need to evaluate the attack on other CPUs, of course,
As well, yeah.
Yeah.
And also we need to notify the users. And custom ROM developers, you also have the problem that if Samsung patches it in their operating system, maybe custom ROM developers don't know about this if this is not publicly documented, right? So it's really important that we publicly document which processors are affected.
Okay, so we have a problem now because we can't store a secret anymore in DRAM. Can we at least store secrets in registers?
Sure, registers must be safe.
Yeah.
Meltdown doesn't attack registers, right?
So with January, ARM also found a closely related Meltdown variant where you could read system registers that are usually not accessible in the current exception level your program is running on. Affected is the Cortex A15, the Cortex A57 and A72. And the impact of this is that you could break KASLR right away, or if you use pointer authentication, for instance, the key would also be stored in a register and you could leak the key with that. Also, we brought a demo with you on the Samsung Galaxy S6. And when we run our attack there, we can see that immediately we can dump all the registers of different privilege levels that our user space application usually has no access to.
Okay, so who is affected by this variant? Intel is affected. We heard first rumors about that in January, but Intel publicly disclosed this in May 21st. In their disclosure, they said that almost every CPU is affected, and they called it rogue system register read. Yeah.
So we talked about Meltdown now. Is Meltdown a side channel attack? Everyone says it's a side channel attack.
I think it's not a side channel attack, and I'm very certain about that. Because for a side channel attack, you would have to use a side channel to read some secret value. And we read the data directly. We directly access it. It does not really work any more directly. We just dereference a pointer and read the value into a register. How can it be any more directly? Okay, we then use a side channel internally for transmission from one realm to the other. But just because we use a side channel somewhere in the process does not make the entire thing a side channel attack. If you have some malware running on an air-gapped system and transmit the data to the outside through some fancy channel, it does not make the entire attack a side channel attack. A side channel attack means that it's much more passive. The victim is not actively manipulated in some way.
Okay, but if it's not a side channel attack, is it a speculative execution at least?
Yeah, okay, so we often heard that Meltdown is speculating beyond faulting instructions, and that's not speculative execution. That's just out of order execution. We're already running instructions out of order that follow after the current instruction. But even if you say, okay, I still want to call that speculative execution, fine. But speculating beyond faulting instructions is not even the actual problem. AMD does that, and they are not affected. It's not the problem that anyone is speculating beyond faulting instructions here. The problem is that we are fetching and using real values for instructions after we are having a faulting instruction. So the problem is fetching and using the real values here.
Okay, we should fix that, I guess, because that's a really, really bad problem here. So we should find out how to fix that. The problem here is in the hardware. So the problem is rooted in hardware. So ultimately, we should fix that in hardware. It's a race condition between the memory fetch and the permission check, and we have to fix that in hardware. And we can also do a hard split of the user space and the kernel space. So that was already designed for ARM, but I guess no operating system used it before, so that the kernel space is not even there if you run in user space.
So fixing the hardware, it's a long-term solution. We cannot just replace all the CPUs right away.
So we need a short-term solution.
Yeah, we need to find something in software.
Yeah.
And the problem are the kernel addresses. Kernel addresses are there in user space, and we can just take those kernel addresses, we don't need them usually, and remove them. If you run in user space, we don't need kernel addresses. We don't We cannot access the kernel. We don't need the kernel there.
The problem here is that the user space accessible check is not reliable in hardware. So our idea was we just unmap the entire kernel in user space, and then the kernel addresses are no longer present. And if they are not present, then you can't translate them to any physical address, so you can't run the attack. If you think back of our operating system illustration, we would switch from this view to a separate kernel view and a user view. And now the user can run the attack, so the user can run through the wall, but there's nothing behind it. So the user can't gain anything from it.
Yeah. So actually we published KASLR in May 2017, but not to mitigate Meltdown, but to mitigate other side channel attacks, because Meltdown was not known until then. And inadvertently, and luckily to us, it also defeats Meltdown. We introduced a POC implementation to the Linux kernel, which we also uploaded in May. And
yeah, it was not that easy, so just unmounting the complete kernel address space is not possible. The architecture still requires some parts of the kernel to be present, like interrupt descriptor tables. If we have an interrupt in user space, for example, because we move the mouse or enter stuff on the keyboard, we still need something mapped in the kernel, so
code,
we can
stacks, different things.
Stuff for context switches, we still need a few parts of the kernel mapped in the user space.
Also, in addition, when we want to switch to the other address space, we need to know the physical location of that. So we need to update the CR3 register with this address, and this address has also to be stored somewhere. And how can we do this efficiently? So instead of one page global directory, we now use two. They are 8K in size and also 8K aligned, and then we can do a nice trick. We can just flip the 12th bit of the pointer to switch between those halves and therefore with those mappings. So as we can see on the illustration at the bottom, we just flip one bit, then we use another offset, which is our other address space, and then we can continue. And therefore, we do not need to store the address somewhere else, which we need to translate and then store in the CR3 register. We can just use the value already stored there, flip a bit, and then change the address space. And this is pretty nice.
So Intel and others improved over our KASLR patch starting from May. We already got first feedback in May, and later on we got also emails from Intel asking us specific things about the KASLR patch, and then finally notifying us that they developed a larger patch set which actually makes this practical for the Linux kernel. It was later on merged into the Linux kernel as KPTI because they didn't like the name KASLR for some reason. Fun fact, KASLR in German is the name of the largest penguin, the emperor penguin, but I think they were not aware of that. So there were also patches for ARM64, and
it's not only in Linux, it's of course in other major operating systems as well. For example, Apple released the updates already in December, I think. And
they had an option for that
on, similar before
on 32 bits.
Yeah, where
this was doing rather the opposite.
Yeah, they didn't unmap the kernel in user space, but the user space in kernel. So that mitigated different attacks. And after this update, they also had the other way around, so they have protections in both directions.
And of course, Windows also has a mitigation, which they call kernel virtual address shadow, and it's their implementation to mitigate Meltdown on Windows.
So introducing such a fundamental change into an operating system is extremely challenging. Our proof of concept had many bugs, it crashed very frequently, and we were very lucky.
Why.
Yeah, we were very lucky that we got the feedback from the Linux community because we were really unexperienced in writing larger kernel patches.
And we had a lot of more time because at this point Meltdown wasn't known, so we didn't have any stress in developing this patch.
And we were also quite lucky in hindsight that we had this patch ready already a few months before we needed it.
So even major operating system vendors with really good programmers made some mistakes in implementing this patch at first. So in the Microsoft version, they had a small mistake in there where they made the page table entries user space accessible. So from a side channel attack, or not a side channel attack, but using a side channel, to leak values from the kernel, they generated a real exploitable bug where you can read and write values anywhere on the whole system. So this was the total meltdown bug in the meltdown patch for Windows, for example.
So what now? How can we go on from here? We expect that there will be more attacks exploiting performance optimizations. We are already seeing new variants, for instance, of Spectre and Meltdown popping up frequently. And I think that this will be even more frequently in the near future.
Yeah. This gives us a unique chance now to rethink our processor designs. Right now, we always optimized for performance, a lot of performance. But maybe we have to also take into account the security and find trade-offs between security and performance for newer designs, designs that are better in terms of security and grow up like other fields did. Like it was the same in the car industry. We didn't get faster and faster cars all the time, but at some point they also made the cars safer than before.
So last but not least, we published our proof of concept implementation of the Meltdown attack on GitHub. You can download it there, compile it, and try it on your machine yourself. Hopefully your machine is already patched, so you need to disable the mitigations to test it.
We will also add new code there that we just showed here in the presentation.
Yeah. So to conclude our talk, in the end, we underestimated microarchitectural attacks for a long, long time. And with Meltdown, we exploit performance optimizations that allow us to leak arbitrary memory, which is a huge problem. The countermeasures that we've seen come with a huge performance impact, so we need better solutions. And therefore, we need to find a trade-off between security and performance, because we cannot have both, apparently, at the same time. Thank you for your attention. If you have any questions, feel free to ask or come to the Q&A afterwards. Thank you.